Digital circuits are the backbone of modern electronics. They process and manipulate information in the form of binary digits, zeros, and ones. Within the realm of digital circuits, there are two primary categories: combinational circuits and sequential circuits. Combinational circuits determine their output based solely on the combination of present inputs. In contrast, sequential circuits add a fascinating layer of complexity. They consider not only the current inputs, but also the history of past inputs to determine their output. Imagine a light switch controlling a simple light bulb. This represents a combinational circuit. When the switch is on, the light turns on. When the switch is off, the light turns off. Now consider a digital alarm clock. It keeps track of time, displaying the current hour, minute, and second. This ability to remember past inputs is what distinguishes sequential circuits. Three key features underpin the functionality of sequential circuits: memory elements, clock signals, and feedback mechanisms. Memory elements. At the heart of every sequential circuit lie memory elements. These elements act as storage units, holding information about past inputs. Latches and flip-flops are the most common types of memory elements. Clock signals. Sequential circuits employ clock signals to synchronize their operations. A clock signal is a rhythmic pulse, alternating between high and low voltage levels. Feedback mechanisms. In sequential circuits, the output depends on the current state stored in the memory elements. This interplay of memory, timing, and feedback allows sequential circuits to perform complex tasks. Sequential circuits can be broadly classified into two main types: synchronous and asynchronous sequential circuits. Synchronous sequential circuits. In this type, all state transitions are synchronized with the clock signal. The memory elements update their stored values only when the clock signal transitions from one level to another. This synchronized operation ensures predictable behavior and simplifies the design process. Most digital systems rely on synchronous sequential circuits due to their reliability and ease of analysis. Asynchronous sequential circuits. Unlike their synchronous counterparts, asynchronous sequential circuits do not rely on a global clock signal for synchronization. Their state transitions are triggered directly by changes in input levels. Section 4. Components of sequential circuits. Sequential circuits are built using two primary components: memory elements and combinational logic. Memory elements. Memory elements are the fundamental building blocks responsible for storing state information. They come in various forms, with latches and flip-flops being the most prevalent. Combinational logic. While memory elements store information, combinational logic dictates how the circuit processes that information and generates outputs. Combinational logic circuits take the current inputs and the previous state to determine the next state and the circuit's output. This combination of memory and logic allows sequential circuits to perform a wide range of operations, from simple counting to complex data manipulation. Section 5. Applications of sequential circuits. The ability of sequential circuits to remember and process sequences of data makes them indispensable in countless digital systems. Here are just a few examples. Counters are the workhorses of digital systems, used in applications ranging from simple event counting to frequency division and timing. They utilize memory elements to store the current count and combinational logic to increment or decrement the count based on input signals. Shift registers. Shift registers are essential for data manipulation tasks. They store a sequence of bits and can shift these bits to the left or right, one position at a time, upon each clock cycle. This shifting operation is crucial for serial data communication, data conversion, and other applications. Memory units. From RAM in computers to flash drives and hard disks, memory units rely heavily on sequential circuits. These circuits store vast amounts of data by arranging memory elements in complex configurations. Finite state machines, or FSMs. FSMs are powerful tools for designing digital systems with complex control logic. They represent a system's behavior as a finite number of states and transitions between those states based on inputs and the current state. Traffic light controllers, vending machines, and digital watches are just a few examples of systems implemented using FSMs. Communication systems. Communication systems heavily rely on sequential circuits for tasks like data encoding, decoding, synchronization, and error detection. Timers, used in countless applications from kitchen appliances to industrial control systems, rely on the precise timing capabilities of sequential circuits. Control systems. Control systems, from simple thermostats to complex industrial robots, use sequential circuits to monitor inputs, make decisions based on predefined logic, and generate control signals to actuators. Section 6. Advantages and challenges of sequential circuits. The power and versatility of sequential circuits come with both advantages and challenges. Advantages: memory. The inherent ability to store and recall past information is a significant advantage. It allows sequential circuits to implement functions like data storage, timing, and sequencing. Versatility. Sequential circuits are highly versatile and can be configured to realize a wide range of functions. This adaptability makes them suitable for a diverse set of applications. Challenges: timing issues. Timing is critical in sequential circuit design. Issues like clock skew and race conditions can lead to unpredictable behavior and design errors. Complexity. Designing and analyzing complex sequential circuits can be challenging, requiring a deep understanding of timing diagrams and state tables. Section 7. Conclusion. The importance of sequential circuits. Sequential circuits, with their ability to remember past inputs and generate outputs based on both present and past information, are the backbone of countless digital systems. They enable functionalities like timing, counting, data storage, and complex control logic, making them essential components in computers, smartphones, communication systems, and a myriad of other electronic devices. While designing and analyzing sequential circuits can be challenging due to timing complexities, their versatility, memory capabilities, and wide range of applications make them indispensable in the world of digital electronics. As technology advances, the importance of mastering sequential circuits will only continue to grow, driving innovation and shaping the future of digital systems.